In this video, I'll be going over the Neber rearrangement mechanism. It's going to include some sort of an oxime. In this case, I've replaced the H that you'd normally see with an oxime with a tosylate group. That's simply done by using something like tosyl chloride um, just to do that replacement. And then we're also going to use base. So that's the difference between Neber and Beckmann. So in Neber, you're going to use base, and Beckmann, you'll use acid. Anyways, when you throw in the base, it will first see this proton that I'm going to call on the alpha position to our oxime group. So if this is our oxime, then maybe this is our alpha position. So the electrons from the base would come over, pull off the proton. The alpha carbon gets those electrons. Redrawing what we have now. Oxime hasn't been messed with yet, but we have that lone pair that's on the alpha position. So we can move these electrons up to hit the nitrogen of the oxime and kicking out the tosylate group. So when you kick that out and it wants to leave because it's a big bulky group, kicking that out, you're going to have our azarine that we're forming. So that's our first big step of this mechanism. So there's our arbitrary R groups and our azarine. Going forward, now we're going to introduce something like an acid. And so I'm going to use just like water dissolved, or hydrochloric acid actually dissolved in water. So HCl and water. So with the electrons from our azarine, nitrogen will come over, pull off the proton from hydrochloric acid. Chlorine takes the electrons. Now we just have a protonated azarine. And it looks like this. And our positive charge. Great. So now we have a bunch of water floating around. So we can kind of let the water do something here. So there's our water, has the lone pair of electrons, and let it attack that double bond position of our azarine. So you can kind of think of this like any other carbonyl that's being attacked by a weak nucleophile. So back in Organic Chemistry 1, we protonated some carbonyls to make them more susceptible to nucleophilic attack if our nucleophile was not that strong. It effectively lowered our molecular orbitals and made it easier for the weak nucleophiles to actually approach. So that is the same exact idea of what we are doing right here. Okay. So at this point, we need to just do a simple proton transfer, and I'm just going to write PT for that. We can probably guess proton transfer is going to take place from the thing that has the charge that I should have drawn in red, the thing that has the charge to our the next thing I can possibly hold a charge. So that's our nitrogen here. So that'll look like this. Just like that. And we have a little alcohol hanging off there on the side. So at this point, we're just going to reform our, or actually form for the first time, the beginnings of our carbonyl. So we're going to let these electrons come down and start that beginning of the carbonyl and satisfy the charge on the nitrogen. Okay, so that brings us down to our next intermediate, which looks like this. Oops, I can draw this better. Probably be nicer to draw it this way. Just like this. And of course, the positive charge. That didn't go anywhere yet. Now if we have enough hydrochloric acid that's floating around, we can do yet another proton transfer and complete our mechanism. So Doing one more proton transfer leaves us with this thing. So our NH2 complexed with hydrochloric acid. Okay, so that would be our full mechanism for the Neber rearrangement.